Hello everyone, my name is Robbie Stewart and I'm a PhD student in the Department of Nuclear Science and Engineering at MIT. And today I want to talk about a structures first framework for cost-effective advanced nuclear technology. I'd like to acknowledge my co-authors Enrique Velez, Ralph Weiser, and Professor Karush Sherbin. So a little bit of motivation and background. 15% of US greenhouse gas emissions are from industrial process heat. And so we need a cost-competitive, carbon-free way to meet this industrial heat demand. So many of you are probably familiar with the metric levelized cost of electricity, but we can look at levelized cost of heat in a very similar way. So these data are from Lazard 2017, and we can see that the levelized cost of heat for natural gas is in the $20 to $40 per megawatt hour thermal range. And wind, solar, and utility solar PV are all sort of the $30 to $60 per megawatt hour thermal range. And there's a fourth carbon-free option here, nuclear, but it's really uncertain where it fits and if it can play a role in this market. And so in fact, in 2005, the Department of Energy launched a program called the Next Generation Nuclear Plant program, and it was really aimed to design and build nuclear reactors to meet the process heat demand in the name of decarbonization. The program selected the high temperature gas cooled reactor, or HTGR, as their technology, and they made the selection for the high degree of passive safety, the high degree of technology readiness, so 2 plants like this had already been built in the US, though it had been decades in the past, and the high temperature heat output capability. The program ended up spending almost $500 million on trade studies and conceptual design, but the plant was never built. And a government accountability report cites 2 primary reasons for this. The first is the tanking price of natural gas from across the years of the program. And the second is that the nuclear industry and the Department of Energy couldn't come to a cost share agreement. And why is that? Why could they not come to a cost share agreement? Well, it's because nuclear projects were having major cost problems in the middle of all of this. If we look at 10 nuclear plants built in the last 20 years, in the US, France, Finland, Korea, and China, we can see that on average, these projects are 2.3x over budget. And if we look at the construction timeline, so this is actual time to build a plant versus the projected time, we can see that on average they are taking 2.4 times as long to build as they're projected to take. And then if we focus specifically on the Western nations, so France, Finland, and the US, we can see that the projects were initially forecasted to cost $2,700 per kilowatt on average, but their actual delivered cost was $7,600 per kilowatt, almost 3x. They're also supposed to only take 4.5 years to build, and they took all 13 years to build on average. So these are huge issues in the nuclear industry. And to top it off, HTGRs, or the type of reactor chosen by NGMP, if you recall, are even worse on cost than traditional nuclear power. They are very large. The reactor core has very low power density, which has great inherent safety advantages, but comes at large cost disadvantages. So if you can imagine, a very large core means a very large building, and a large building means a large cost and large construction time. So to look at an example of this, this is the AP1000, which is a water-cooled sort of state-of-the-art reactor designed by Westinghouse. And it's 1,100 megawatts of capacity. And if we look at how much capacity they have per volume of safety grade building, this is sort of like a building power density. They have 7 kilowatts of power capacity per meter cubed of safety grade building volume. And so you can think of safety grade building volume as sort of a surrogate for cost and time it takes to build. The plant selected by the NGMP program was the SCHTGR, was Areva then, now Framatome, and it was a 4-unit, 275 megawatt electric per unit plant, and it had 2.2 kilowatts per meter cubed of safety grade building volume. So like a third of the power density, or in other words, the buildings would be 3 times as large, which is not the direction we need to be moving for cost and construction time. So let's dive a little bit deeper into this cost problem. In 1987, the Department of Energy published a database called the Energy Economic Database, and it was detailed cost information for a 4-loop pressurized water reactor, PWR, almost 1,200 megawatts, 1,144 megawatts of capacity. And they broke the costs down into a code of accounts system. So these 6 accounts are how the costs were categorized. And we've sort of assigned the indirect costs proportional to the amount of nuclear work in each direct cost category to simplify the view here. And typically nuclear engineers focus on reactor plant equipment. This is, it's the largest cost category here, it makes sense. But if we look at EEDB, it actually shows that the average cost overrun in this account was 20%. But the average cost overrun in account 21, structures and improvements, was 50%. And we can sort of further confirm this by looking at those 10 reactors I showed in the beginning. Just 2 quick examples. One is that the Olkiluoto plant in Finland was delayed 9 months for having too high of water content in its concrete castings. And then the Vogtle plant here in the US was delayed to a soil compaction miscalculation. And so our thesis here really is that we need to shift our focus from account 22 to account 21, because these are really where the problems and delays and overruns are being driven out of. So we introduced our structures first framework for design, and it led us to MIGHTR, a modular integrated gas high temperature reactor. And we really see it as a more optimal HTGR. So let's look at another state-of-the-art HTGR. This is the HTR PM under construction right now in China. It is in a 65-meter tall building. It has an overhead crane that is used to install the primary components. The reactor core is where the heat is generated. And then the steam generator is where that core heat turns water into steam to power a turbine. But if we look at this building, we can see a lot of spaces that seem suboptimal. There's a lot of building volume here that seems unnecessary. So this overhead crane, which is maybe a 1/4 of your total building volume, is really a low utilization crane. Because of the way that they have offset the core and steam generator in the reactor building, you have a lot of wasted space above the steam generator. And because of this really tall building, you have a lot of space dedicated just to mechanical lifts and stairs to move people and equipment up and down the building. So with MIGHTR, we actually integrate those large primary components, the core and the steam generator, into one singular vessel. We turn the whole system horizontally to eliminate the overhead crane. And now instead of having to bring our parts in and use the crane to rotate them, to install them, our parts just come in as they are to be installed. And both of these save a lot of building space and therefore cost. So a few more details. The large segments, the core and the steam generator, they're flanged together. A rail-based system on the ground actually eliminates the overhead cranes, and that rail-based system doubles as the support system for the core and steam generator once they're in place, and the dual use saves space. Our building is only 10 to 15 meters tall, which makes the geotechnical risk much lower and the site prep and investigation much easier. Further, the shorter building makes it much easier to embed or put underground, or even surface mount if you want to put it half on the ground and bury it. And the shorter building makes construction time a lot shorter because of the shortened concrete curing times. So back to our metric of building power density, we envision MIGHTR as a 4-unit plant similar to the SC-HTGR. And if we look at the AP1000, recall that it was 7 kilowatts per meter cubed. The SC-HTGR was 2.2 kilowatts per meter cubed. And now MIGHTR comes in at 7.6 kilowatts per meter cubed. So we've sort of achieved the building volume power density of the water-cooled plant, but we get the high temperature and the high temperature and the passive safety of the gas-cooled reactor. So a little analysis and discussion. So we did some cost estimating of our idea. I won't spend a ton of time here. There's more details in the paper. We used sort of the classic cost scaling power law to scale each cost account individually. And then we use different base units and scaling exponents for each account. That information is in this table. Again, there's more details in the paper. And then we correct for the expensive HTGR reactor equipment because it's much larger. We correct for the type of safety grade building. Is it a airtight containment? Is it just a reactor? Is it like just an auxiliary building? And then we correct for sharing auxiliary equipment if there's multiple units. And so we get nth of a kind cost estimates for the MIGHTR, and it comes 25% lower than the specific cost estimate for the SC-HTGR. And this is really the cost value that we've been targeting. The other thing is for a first of a kind plant, MIGHTR as a 1 unit versus the SC-HTGR as a 1 unit plant versus the AP1000 as a 1 unit plant, the financial risk is substantially lower. So MIGHTR comes at about $1.1 billion for first of a kind cost, whereas the AP1000 is over $7 billion. And so that means when you hit that 2x cost overrun, you're only down an extra $1 billion, which is still a lot of money, but it's much better than being down another $7 billion. And a key element here, if you look at this bar chart on the bottom, is that MIGHTR has shifted the bulk of the HTGR cost from structures and improvements to reactor plant equipment. And again, this comes to our metric of structures drive delays, cost overruns, and that's backed up by recent experience in Finland, France, the US, also historical experience in the Energy Economic Database. And so by shifting the costs from structures to reactor equipment, we think that we've lowered the risk for the project and we've enhanced the likelihood of meeting the schedule, the projected schedule. So what does this mean for our levelized cost of heat? Back to the first slide for this industrial process heat market. We forecast that MIGHTR could fit in the sort of $27 to $35 per megawatt thermal range, which puts it just as, if not more competitive than the rest of the renewables, and then right in the middle of the range for natural gas. So we think this could be a really exciting technology for decarbonizing the industrial process heat market. So to summarize, MIGHTR is a low-cost, near-term, carbon-free source of power, and it came out of this structures-first design framework. By targeting the types of engineering that cause delays and cost overruns, we've come up with a sort of an optimized HTGR design. We've horizontally oriented everything to facilitate installation. We've integrated the large components to make everything more power dense. And then we've done this all in a much shorter building to accelerate our construction schedule. So with that, I'd be happy to take any of your questions. I'd also like to acknowledge the sponsors for this project, EDF and RPE. Thank you.